Good morning everyone. I am Dr. Senthilkumar, Professor in EC Department, BSB Engineering College, Karur. Today we are going to see the Unit 2. It is Lecture 2. The course name is Digital Principles and System Design. In that we are going to see Unit 2 topics. The main heading of Unit 2 is Combinational Logic Circuits. So this is the overall syllabus. In that we are going to see the content in combinational logic circuit. So these are all the topics that we have to cover under this topic. So what we will learn from unit 2. The main heading is, as I told, it is combinational logic circuits. In that the subtopics are design procedure, that is for combinational logic circuits, half adder and full adder, half subtractor and full subtractor, magnitude comparator, encoder and decoder, multiplexer and demultiplexer, finally code converter, that is binary to gray and BCD to XS3, and we will do reverse code conversion also, that is gray to binary and XS3 to BCD. So these are all the textbooks available here. Okay, so I request the students to take a note of these textbook and reference books for further reference. Okay, so as usual, now we want to see what is course objective. So according to the requirement of curriculum, these are all the course objectives. To facilitate understanding of logic gates and minimization techniques. Actually this is for unit 1. Now we are in unit 2. So this is our course objective as of now, to guide design of simple combinational logic circuits, and the remainings are for the remaining units, that is third, fourth, fifth units that we will see in the coming videos. And of course the next is course outcome at the end of unit 2, that is end of this presentation. You have to understand the designing and implementation of combinational circuits. This is the requirement. Now again, as per the requirement of NBA, these are all the program outcomes. First one is engineering knowledge and problem analysis, design and development of solution, conduct investigation of complex problems, modern tool usage, engineers and society, environment and sustainability, ethics, individual and teamwork, communication, project management and finance, lifelong learning. So these are all the 12 outcomes, that is program outcomes that we have to follow up in this curriculum. Now, of course, this is the PO, COPO, PSO mapping. Now we are in the unit 2. So this is the required COPO mapping. These COPO mappings are, the numberings are chosen according to the relevant COPO mapping categories. As you see here, so if 3 is given, it is highly mapped, and if it is 2 is given, it is moderately mapped or mediumly mapped with the corresponding CO and POs. And in some cases you might have seen 1, it is lightly lowest mapping here. Okay, this way the COPO mappings are given. PSO, program specific outcomes, are chosen according to our own unique curriculum. Now we come to the main topic. As per unit requirement, the main heading is combinational logic circuits. So in this we are going to see the design procedure. Again, a design procedure, adders and subtractor, comparator, encoder, decoder, multiplexer and demultiplexer, and finally code converter. These are the topics that we would like to cover in this presentation. Now, the first topic. So, this is the block diagram of combinational logic circuit. So, this is the block diagram of combinational logic circuit. So, you see the definition here. It is the definition for combinational logic circuit. A digital logic circuit where the output at any instant depends only on the present combination of input values with no reliance on past states or memories. Usually the past states and the memory elements are required for sequential circuit. That is another kind of digital circuit. Okay, now we are in combinational circuit. Kindly keep a note on that. We only have a this simple block diagram, that is the present output only depends upon present inputs. We need not to worry about the past states. Okay, the key characteristics are given here. It is the memoryless operation, that's why we told there is no need of flip-flops and latches. It provides same input always for the respective outputs. Okay, it is expected for the purpose of combinational circuit. Instantaneous response. It is expected to provide immediate response when the input is given. No feedback loop. Okay, it seems there is no feedback between output and input. So this is the major requirement of combinational logic circuit. We will see one by one. I request the students to understand, keep these things in your mind while going through the remaining topics. Always you look into that. There should not be any memory element, and it should the output always produce the unique output. Okay, so according to the given input, and there should not be any feedback also. There is no connection between or feedback link between output to input. Okay, now we go to standard design procedure. So in the case of combinational circuit design, there is a systematic procedure. Okay, so the steps are following like this. First, you have to define the problem specification. Okay, so what is the purpose we are designing the circuit? Next one is input output definition. There should be the proper definition for what kind of output we need for the respective inputs, and based on the required input and output, the truth table is to be constructed. Then we have to go for Boolean expression derivation as a function. Then we should do the simplification procedure. So some kind of simplification procedures like K-map we already discussed, okay, in the unit 1. Okay, based on the any simplification procedure like Boolean algebra or K-map, you can do the simplification, because the ultimate requirement is we should have a efficient digital system design at the end. Efficient in the sense it should be very compact. There should not be any much power consumption, and the number of gates used for the designing of implementation should be as much as possible reduced. Finally, we should go for implementation and verification. Now, this is the very first circuit, that is called half adder design. So in the half adder you could see, okay, it is expected to be only two inputs and the corresponding outputs are given here. Then finally, based on the this is called truth table. Based on the output column, okay, identify number of ones, accordingly the function is described here. Okay, if one is here, there are two ones. I show you how the function is described here. If one is in the sum, okay, the yes meant for sum. If 1 is here, this because of this one you are getting here 0, so a bar is coming here, 1 b is there, so it is a sum of product, so a bar b. For this one, this is a bar b. For this one, there is another one here. For this, since 1 is here, the a is coming here, 0 is here, the b bar is coming. Accordingly, the final derivation is a bar b plus a b bar. So this is the function of XOR gate. Okay, so either you can implement with the basic gates like NAND, AND gate, NOT gate, OR gate, you can implement the function, or else with the help of simple logic like this. It is derived from Boolean expression. Okay, so by means of XOR gate also you can uh, implement the function like this. Okay, next is to talk about carry. So here when you see the column of carry, here there is only one. So this is relevant to this input literals. Since under a there is one, the a is coming directly, unless look at here, if for this one here 0 is there because we are putting b bar. But for this a, since one is here, directly a is we are putting here. For this one, now we are in the deriving the function of c. So here one is here, so it is comes under b, so directly you can put b. So this way the function SOP function is framed. So of course this is the application. LSB, least significant bit addition in binary adders. We are using this module like a half adder, and calculating partial products, then it can be the building block of ALU also. So this is the implementation circuit here, direct implementation. So this is the procedure. First, as we see in the last slide. Okay, so the requirement is like this. First, you have to identify number of inputs and outputs. Then you have to put list out all the possible input combinations. Okay, then corresponding required output we have to specify. Based on that, by applying Boolean algebra logic, either you can derive the function like SOP format or POS format. You can have a function like this. This is the function for, or in the form of SOP, sum of product. So accordingly, finally you can have a logic diagram like this also. Okay, so here since the symbol here is XOR gate, you can use the XOR gate like this. Then here it is AND gate, so you can use the AND gate logic symbol like this. Then you can implement the function. Okay, so see here, there are two inputs, A and B are input literals as you see here also. So since A is given here, B is given like this here, so this B is common to AND gate also as you see here, so that the implementation is given like this also. The final sum and carry implementation is being done like this. Okay, so this is the very first example to implement the combinational logic circuit. Okay, so we will go to the next version of combinational circuit. Now you see full adder. This is the full adder design. So in that you see the number of inputs. Now here there are three inputs apart from A, B and C in, carry in also the another input. Because of third input is coming in, here it is called as full adder. Okay, so this is the overall possible combinations for full adder input. So these are all the required output. As a user, we have to design the required output for each and every set of input. Note here it is unique. Okay, unique in the sense the output defined for one particular set of input should not be repeated again and again. Okay, this the user has to maintain properly. Okay, the while designing the or putting the truth table illustration, you have to do the procedure properly. Okay, this is the primary requirement to design the truth table. Okay, now as I told, now to design the or implement the function, you have to look into the output column. Here there are 1 2 3 4 ones. Accordingly we have to define the function in the SOP format. And for the count also there are 1 2 3 4 ones. Then finally the count function is derived like this. Now you see the corresponding implementation, circuit implementation. See here there are two XOR gates, so two XOR gates are coming in, and then AB providing a XORed with another C in, so that you will have yes according to this requirement. And for C out, it should be the diagram like this. Okay, see here for AB there is a AND gate, and C in ANDed with A X or B. Okay, so that you can see the diagram like this. So it already available like this here, and A XOR B, C in is provided here. So totally this is and C, because of this plus the XOR gate, sorry, OR gate is coming in like this. Okay, now you see the applications. It is the multi-bit binary address. It can be used as a multi-bit binary address, arithmetic logic units. It can be used, ripple carry counters. It can be used. Similar way we are going for half subtractor design. So this is the necessary inputs, this is the necessary outputs. Okay, so again to derive the function you have to look into the output column like this. Okay, then you have to do the implementation. Uh, Fortunately here you see the same structure what we had half subtractor for some comes here also, so there are going to be much complications here. So when you see the barrow structure, it is like this. So the implementation is to be done like this. Since one is here, it is a bar B, and only one is available. So only one term will come here. Accordingly, the design procedures are being done. So this is a full subtractor design. So this is the block diagram. Okay, you can see here there are three inputs and two outputs. So this is the required truth table. Since there are three inputs, okay, unlike in half subtractor, here one more input is added, that is borrow in. So since borrow in is coming, there are three set of inputs as you see here in the block diagram. Okay, now accordingly there are eight different unique inputs, then there will be the unique eight different outputs also. So as you see here, okay, so now we going to design the or implement the function according to the function. Again this is the SOP format. Look at here. So based on the number of ones, as we told already in the design of FADR, so that is the basic idea to behind any design, any kind of combinational design. Once you want to design any function, or you want to implement or describe any function in SOP format, you have to look into the number of ones in the output column of the particular design. Accordingly, you have to give the terms in the function area. So this is the requirement you see here. So this is the derived expression. Okay, as you see here there are two XOR function. You can see the implementation here, there are two XOR. Now it is easily understandable here. See there are um, 1 2 3 4 ones are here. Okay, again it has been simplified like this. So based on the number of ones, we are going to have a final function after the simplification. Now this is the final function. So accordingly this implementation circuit has been done. So this is the full subtractor design. Okay, again I wish to recap the design procedure here. So first thing is you should have a block diagram like this. So in the block diagram you have to specify a number of inputs, number of outputs required. Now come to the truth table. In the truth table you have to provide all possible combination of inputs according to the chosen block diagram. Okay, here there are three inputs, so here it is mentioned like this. Then accordingly we have to identify all the possible number of inputs. Okay, possible combination of number of inputs, then we have to specify correctly number of outputs. Okay, every set of inputs there should be the output. Okay, it should be mentioned properly. Then we have to go for the function implementation. Function can be either SOP form or POS form, that is a sum of product or product of sum. Here we are choosing sum of product. Okay, so accordingly the derivation has been done for the function. If simplification is possible either by means of Boolean algebra or K-map, you try to do it and you put the final function for the derived final function, then you go for the implementation. So this is the overall design procedure for any kind of combinational circuit. So I request the students to keep these things in your mind for the further complex combinational circuit design. Okay, now we move on to the next topic. Now another version is called magnitude comparator. Here a single bit magnitude comparator design has been provided, but with the help of this idea you can do any n number of magnitude bit n number of magnitude comparator. Okay, so this is a single bit magnitude comparator design. So look at the um, truth table for that. See, as you see here, this is the input side. Since it is single bit comparison, either we will be comparing 0 with 0 or 1, or 1 with 0 or 1. So this is the maximum possibility we can try with single bit magnitude comparator. Accordingly, the outputs are provided. So the maximum possibility of comparison could be like this. Output like either you can have a less than b, or a equal to b, a greater than b. Okay, so if a less than b is when it will possible, when a is 0 b is 1, then it is possible a less than b. So a equal to b when it is possible, when a is equal to b, that is both are 0 or both are 1, then a is equal to b. So here one is provided, here one is provided. So a greater than b in the sense here it is possible. Okay, when a is 1 b is 0, then a greater than b is possible. In particular point we have to provide 1 here, so remaining conditions are 0. Okay, so accordingly we have to clearly specify the output. Okay, there should not be any conflict in the design while providing the outputs. Okay, if there is a conflict exist, then it will impact in the final implementation. So while defining the output to the corresponding input, we must ensure that we are providing the proper unique required outputs. Okay, so then only you can have a final circuit implementation properly, otherwise it may have a error. Okay, so now you see here for a less than b, for here it is inversed. See here a greater than b. Look at here a greater than b. Only one is there. That is since one is here, it is a b bar. Okay, you see here. Now we are seeing encoder and priority encoders. Okay, so this is the 3823 priority encoder block diagram. So here you can see the corresponding truth table. As you see here, there are 8 inputs from D0 to D7. Here it is mentioned in the truth table, it has been mentioned. Okay, so here D0 to D7, the possible inputs are like this. So you see here the new unique representation that you could not see in the previous slides. See here, it is x. X is nothing but, in the terminology of digital system design, it is don't care state. Okay, so whatever may be the value here, see, since the binary values are taken here, either x can be 0 or 1. The thing is, regardless of the values here, if in D7 1 is there, the expected output should be like this. Okay, so here in the block diagram it is noted that q0 q1 q2. Here in the truth table it can be y0 y1 y2. So q0 will be equal to y0, q1 will be equal to y1, q2 is equal to y2. Okay, see here there are 3 outputs. In the truth tables also it is mentioned at 3 output. Okay, so the priority in the sense, regardless of these values, okay, regardless of these x values, it can be either 0 or 1. If D7 is 1, so the output should produce, this is the output, these values, okay, 1 1 1. Similarly, in this case, you see here, if it is 0 in the last row, you see that everything is 0, but if uh, D naught is 1, then the output should be 0. Okay, so this is the thing, it is mentioned in priority encoder. So when you normally, wherever you see the priority encoder, in the truth table there could be some x's. If x is not provided, instead of x, the definite value like zeros are mentioned, it is normally encoded. Wherever you see the x values, that is don't care states in the encoder truth table, that is meant for priority encoder. Or else if x is not there, then simply it is the encoder. Okay, so this is the implementation circuit. As we discussed already, to implement the final circuit, we have to look into the ones in the output column. See here, there are 4 ones. It is relevant to D7 and D6 and D5, D4. Okay, accordingly you can see the output. Okay, so why not, you see here, in the Q2. Okay, you can see the output here. Okay, D7 and D6, D5, D4. Okay, so these values are given here. Okay, so accordingly you can implement the design. Now we see decoders. Okay, so in the previous slide, we could see 8 to 3 encoder. Now we see the vice versa, that is 3 to 8 binary decoder. So this is the possible application of this decoder. You can see normally this is the configuration for LED, 7 segment LED. So with this idea, you can implement functioning of a 7 segment LED. Normally the 7 segment LED will have 7 segment, 1 2 3 4 5 6, and the G is also available here. This is the 7th segment. So to eliminate the LEDs in the particular segment, we have to activate or provide the corresponding binary values to the particular value. For example, you see here, now we are talking about the application, and then we go on to the design. After that, see here, if you want to eliminate the digit 0, look at here, A, B, C, D, E, F. This is to be eliminated. See, every segment should provide a certain value. Okay, according to the design requirement, either you need to supply 0 or 1. Okay, so accordingly the elimination will happen. If this get the corresponding elimination binary value, then it will be eliminated. Similarly, for B segment of B, if you want to eliminate it, you have to provide appropriate value. So likewise, everything is possible. So look at here, if you want to implement 8, okay, you have to eliminate all the segment of 7 segment LED. And for that, you have to provide all necessary values to the all segment. Okay, accordingly it will eliminate. Okay, so this is the implementation requirement for 7 segment LED. Likewise, so many applications are there. This is one of the basic usage of decoder, especially 3 to 8 binary decoder. You can see the truth table for this. Okay, so as we see here already, see, this is a 3 input, 8 output. Okay, so 3 inputs are there, ABCs are 3 inputs. So 2 power 3, 8 different possible combinations are there. So accordingly, for every input segment combinations, you will have a different outputs like y0, y1, y2, y3, y4, y5, y6, y7. Okay, so accordingly you can provide the necessary output. Okay, so this can be effectively used to eliminate the 7 segment LED. This is the possible application. I request the students to go further on this design procedure to better understanding of application of 3 to 8 binary decoder. Likewise, you can do higher version of binary decoder also. Okay, so here for sake of simplicity we have used 3 to 8 binary decoder. Since we are providing three inputs, what you have to specially understand is, uniquely understand is, see here, if three inputs, we have provided 8 different possibilities. If you are, instead of 3, if you are using 4, then there could be 16 different possible combinations. Accordingly you can use it for some other purpose. Okay, so this is the application of decoder. So in the previous case, when you see here, see in the case of encoder, see input is high numbers, output is low. Okay, 8, here it is 3, but unlike that, here you can see in the decoder, so a number of input is less when compared with number of output. This point you should understand. Rest of the things are similar. Okay, that way we have to implement the decoder. So the possible applications here provided: address decoding. Okay, digital clocks, in the calculators normally decoders are employed much, and instruction decoding in CPU. Okay, central processing units of the computer, these are playing the vital role. Now we are going to see multiplexer. In simplicity it is called as mux. So 2 is to 1 multiplexer, in the sense there will be two inputs, one output. Okay, so here another version, so 4 is to 1. So here there will be 4 number of inputs, there will be only one output. Normally in every multiplexer there will be only one output. Okay, this is the uniqueness in this mux. Okay, so this is the truth table. Normally there will be the select lines. Based on the select lines, the particular input value will come into the output side. Okay, so here it is given, since there is only two inputs, either of the inputs should come to the y, only one select signal is enough. Okay, so this design procedure, in the previous case we never used select signal, but when you come to the mux and demux, we have to talk about, or we have to incorporate the select signal also. Okay, since only there are two inputs, so in particular circumstance or event, either of I naught I1 should come into the y, only yes one signal, select signal is enough. With this, if 0 is there, I naught will come to y. If 1 in the select signal, then I1 will come into the y. Okay, so this is the design procedure for 4 is to 1. Since there are 4 inputs, at one point of time any one input among these 4 should come to y. So the select lines are increased to 2, so that you will have 4 different combinations like this: 0 0 0 1 1 0 1 1. So it seems that whenever you have 0 0 in the select lines, then I naught will come into y. If 0 1, the I1 will come in to the y, and 1 0 I2 will come into y, 1 1 I3 will come into y. So this way the design procedures are happening for mux. Okay, so then the applications are being like this. Okay, it can be used for data routing, parallel to serial communication, logic function generation. Okay, so in that case we are using multiplexer. Now come to the demultiplexer. So here you see the representation here. In the demultiplexer, input is always 1. In the case of mux, output is always 1, but in the case of demultiplexer, input is always 1. Okay, 1 is to 2, 1 is to 4. So here, based on the number of outputs, in the previous case, based of number of inputs, we have chosen number of select lines, but in this case demultiplexer, number of outputs, we have to choose appropriate number of select lines. Okay, here again 1 is to 2 demux, there will be only one line is enough. Okay, so there will be the input, see, based on the value of the select line, the particular input should come to either which kind of output. That means, okay, so for example, if select line is 0 here, then d will come into y naught. Okay, so suppose if s is equal to 1, the d value will come to y1. So this is the case for demultiplexer. Similarly here, as we discussed in the last case, so since there are 4 output, the d value should come into any one of the 4 different outputs. Okay, so 0 0, if select line is 0 0, then d will come to y naught. If select lines are 0 1, D should come to y1. So if it is 1 0, that select lines are 1 0, then y2 will carry D value. And if 1 1, y3, the output line of y3 will carry the D. Okay, so in this way the design is happening. So normally it is used as a data distributor. Demultiplexer are used as a data distributor. The main applications are converting serial data streams into parallel data buses, addressing decoding, okay, selecting memory banks or input output devices in the microprocessor system. So this is the application of demultiplexer. Now we come to the final topics of unit 2. So here we have to talk about code converter. According to your syllabus, you have two different code converters only. One is binary to gray code and binary to XS3 and vice versa. Okay. So apart from this, some other different code converters also available. But here, according to our syllabus, we are going to see only two different code converters. So now come to binary to gray code. So here we are going to talk about 4-bit code converter. Okay, according to the requirement, we can go with 2-bit converter, 3-bit converter, 4-bit converter, even we can go for 5 6-bit converters also. But in general understanding, we have a 4-bit code converter. Okay, so now binary to gray. Okay, so you see here, so this is the predefined required output. This is the predefined required output. That is if this is the set of binary inputs, this should be the set of binary gray code output. Okay, so similarly it is predefined. According to this requirement, we want to design the final logic diagram like this. Okay, so you see here, so again this function is described based on the outputs. You have to see the output column, then you have to go for the function description, then we have to go for the implementation. You see here, see how you are getting G3 is equal to B3. See, when you see here, okay, when you see here, so wherever there is by function itself you can find it out, but when you refer the column itself you can easily identify. See, in the B3, in the last two rows only uh, having 1. Similarly here also it is there, so easily you can put G3 is equal to B3. Okay, so rest of the things are can be derived as we discussed in the previous cases, like when we talk about half adder, full adder design. Okay, how we implement the function and how we made a simplification. Similar procedure here also you have to adopt. Okay, so here for the simplicity we have put the final derived expression. I request the students to go through the detailed description, and you have to work out how to find it out. Okay, so this is the final result. To find G2, B3 is XORed with B2, G1 is B2 XORed with B1, G0 is equal to B1 XORed with B0. Okay, this is the derived final expression. Okay, so you see here, see, you have to go through all the columns. You have to find the ones, number of ones available there in the output column. Accordingly you have to frame the function from the detailed function. Normally we call it as a standard function or canonical function. From that you have to have a final expression like this. Okay, so this is the final expression. So for that the corresponding logic diagram has been put like this. Okay, so G3 is equal to B3, so the line is like coming like this. Directly you can take a line. For getting G2 you have to have a function like this. B3 is XORed with B2. B3 is coming here, B2 is available here, so you can make a XOR function like this. Finally you can implement like this. Okay, similarly other things are implemented. So the applications are provided here. It can be used as a rotary position encoders. Okay, it can be used for K-map simplification. It can be used for clock domain crossing. Okay, so these are all the possible applications. You can use it for a binary to gray code converter. Okay, so now we move on to the another vice versa function, that is gray to binary converter. Okay, So in the previous case, what was the output should come into the input, what was input come into the output in this case. So this is the vice versa. As I told already, this is the required predefined function. You cannot change it. Okay, as far as gray code is concerned, this is the set. Okay, so you have to take as it is. You cannot change it. Okay, it is a predefined function. You have to take as it is as required by the design. Okay, if this set of gray code, then it should be the binary output. If this is the input, this is the output. It is mandatory. You have to have a look at this. You have to maintain the proper set binary set or binary code as per the requirement. You cannot change it. That you should understand. Now come to here. See again, when you see here, what is the things available, what are the binary values in G3 will come here also. Similarly, it is B3 is equal to G3, and now you look into the B2 value. B2 is equal to B3 into G2. Okay, so you can take the representation from the logic derivations, Boolean algebra and simplifications. So this is what here we have put the final expression. In the final expression, this is the result for grade to binary converter. So accordingly, the design, logical design has been done. Okay, for B2, so B3 XORed with G2. So already B3 is available here, then G2 is coming here. So for the B1, B2 XORed with G1. So the result is already available for B2. So this is the B2 result. Look at here. B2 is a result of this. Okay, so that you have to take a line from here, and G1 should be XORed with. These are the XOR gates. Okay, so accordingly the implementation has been done. So this is the simplified logic diagram for grade 2 binary code. Look at here, we have again used only 4 bits. Okay, this is the table for 4 bit. Okay, so that the required logic function is simplified. Logic function is like this. The corresponding logic diagram should be like this. Okay, so this is about grade 2 binary converter. Now come to BCD to XS3 converter. As name itself shows that normally BCD in the sense binary coded decimal. Okay, so this is the decimal value. The corresponding binary coded values are given here. For example, if 5 is the decimal value, the corresponding binary coded decimal is 0101. Okay, the corresponding XS3 value will be here. So 5 plus 3, XS3 in the sense decimal value should be added with the 3. 5 plus 3 is the 8. You can see 8 is the 1000. So it comes here like this. Okay, so normally 0 is that, plus 3 is 0 plus 3, you can have 3. So the corresponding 0011 will come here. 1 plus 3 is 4. This 4 value will be here. Likewise, you can verify yourself. Now again the procedures are similar. That is, you have to have a function from looking into the number of ones in the output column. Accordingly, the Boolean logic has been derived. This is the final expression. So again, I request the students to derive their own function. Then you can verify the result with our presentation. Okay. So this is the final result we are showing here. So look at here, for x naught it should be b naught bar. See here hyphen is there. This is nothing but implement complements. Okay, you have to use not gate to implement this function. B naught is complemented, then you will have a b naught bar. Okay, so this is the function for x naught. You look at the diagram here, how the x naught diagram should be. So you find the major difference between this is XR. Okay, so this is XR gate symbol. If a dot with circle being like this, then it is x naught. So this is the implementation. Okay, so likewise you can do the implementation. So this is the simplified procedure to do the BCD to XS3 converter. Okay, so the applications are self complementing codes for error detection. Normally these type of codes are used for error detection in communication engineering, and normally it was used in older digital computer. Nowadays there is so many advanced techniques. So now we are using advanced code converters. Okay, it is the early stage code converters mainly used in old computers, in calculators, to do the particular operation. Now come to the another vice versa operation. Okay, so here what as I told already, what is by digital value will come here, we have to put a minus 3. Okay, that is enough. Here it is, if it is 0, then the corresponding decimal value should be like this. Okay, so similarly for 9, so easy to understand is just you see the previous slide. Okay, now we come to the summary and conclusion part of this unit 2. Here we see applications overview. Okay, so where we can use these kind of modules. Okay, so now the adders like subtractors, half adder, full adders can be used in arithmetical logical units of computer, and multiplexes, demultiplexes can be used in data routing and control. Again, it is in computers. Okay, so encoders, decoders can be used as an interface device, and as I told, it can be used as a 7-segment LED, for example the decoder. Okay, it is one kind of display device. Likewise, so many display devices are available, interfacing devices are available, wherein you can use either encoder or decoder according to the requirement. Finally, the code converters. See, normally there are so many code converters are available. According to our syllabus, we have seen only two different code converters, that is gray code converter, XS3 code converter. This is normally used for signal processing in data transmissions. Okay, sometimes it can be used for error detection. Some special codes are available, like Hamming codes. This can be used as a error detecting correction code also. Okay, likewise and the application can be described. Okay, so this is the design and optimization tips. Okay, so normally we have seen only limited requirement design procedure for combinational circuit. When you go for commercial products of combinational circuit, we have to look into these design and optimization tips and techniques. Okay, so logic minimization, as I told already, we have to have a effective digital implementation. It seems that we have to reduce the number of logic gates and components as much as possible, so that we can have a compact in our design, as well as the power consumption will be less, delay can be less. Okay, the performance can be improved. So this is the major requirement in the designing of digital logic circuit. We have to give much importance while designing any kind of combinational circuit. Okay, next we should have a critical path analysis. So the as I see here, the propagational delay is the major issue if any path conflict arises. So path in the sense where the data flow happening among the input and output. Okay, so we have to have an effective mechanism to avoid the complexity in the path flow or data flow when the prescribed or designed the path. Next, hazards prevention. So we should not lose the data while maintaining the systematic design. We have to avoid and we have to ensure that there should not be any loss of data. It may also lead to the malfunctioning of the particular design. So we should avoid such kind of hazards in the designing. And finally, the universal implementation. Normally, as we discussed in the unit 1, NAND and NOR gates are mainly used for the purpose of implementing any kind of gate. Okay, in the sophisticated design, normally NAND and NOR are only involved, like VLSI design. So we have to ensure and we have to have a effective system to implement our design. Okay, design procedure with the help of NAND and NOR gate. Okay, so our design must compatible to design with NAND and NOR gate, since it is called universal gates. With that you can implement any kind of gates. Okay, any kind of design also possible with NAND and NOR gates. Okay, so this is the summarization of the unit 2, and I request the students to refer the textbook, given textbook, and reference books for the further knowledge on this unit 2 content. Thank you.